Good morning, good evening everyone. For today's presentation we'll be looking at the ranking systems used by the AFLW and the A-League. The seasons that we're going to be looking at are the 2017 and 2016-17 seasons respectively. To best understand the impact of different ranking approaches on the produced rankings, it's important to first consider the current method being used. At present, both the AFLW and the A-League use a points tally approach that allocates a value to wins, losses and draws. At the conclusion of every season, these point values are added together and the teams are ordered from highest score to lowest score to generate rankings. The two sport codes in focus use different points values. The AFLW considers a win as 4 points and a draw as 2, that is half a win, and the A-League, however, considers a draw to only be worth a third of a win, that is, a win is 3 and a draw is 1. The eigenvector approach provides another way of ranking teams in both sports. This method uses concepts based within linear algebra to produce a rankings eigenvector, derived from the highest eigenvalue. As part of embodying this eigenvector approach, it was significant to consider what value would be attributed to a draw result. As part of this investigation, a 0 and a 0.5 draw value were considered. In this instance, both 0 and 0.5 had no impact on the rankings produced by the eigenvector approach. It was, however, seen more fitting to use 0.5 as a value for a draw, as it aligned with the proportionality of points allocations within the AFLW. With respect to the points tally approach, significant variations were present between the two methods. 6 teams experienced a level of variation as a result of the change in approach. The most significant difference was visible in GWS, who moved up 3 ranks as a result. Similar investigation was done for the A-League. Here the values of 0, half and a third were considered for a draw. Again, a similar logic was embodied. This logic led to a draw being considered as a third. In comparison to the points tally approach, it was observed that 4 teams experienced a change in rank. Of these changes, all were within 1 rank of the original placement on the ladder. The A-League competition sees teams play each other 3 times over 3 rounds. To accommodate this, the augmented matrices generated at the end of each round were added together to create a matrix representing the full season. This matrix was normalized before using MATLAB to generate the ranking eigenvector as per the previous computations. Based on this approach, 5 teams were ranked differently, the biggest change being a change of 2 ranks.
When considering the possibility of introducing a new point system where large wins are recognized, first we had to establish what a large win meant. As we were using the 16-17 season of the A-League, we considered a large win to be greater than or equal to 3 goals difference. The next step was assigning how much those wins would be worth. We investigated 2 systems, the first shown in figure 4.0, where a large win is worth twice the amount of competition points as a small win. The second introduced a bonus point system, where teams would receive an additional point in the case of a large win, shown in figure 4.1. When we put the data through these systems, we were able to observe that they both showed significant differences from the original ladder. We settled on the most useful being the bonus point method, as the 6-point big wins introduced the possibility of an outlier big win skewing the rankings too much. By adjusting our win, loss, draw matrix to include a 4/3 evaluation for a big win, this would maintain the same proportionality as the points tally approach. The results of this again showed difference to the original rankings. When positioning all the new systems next to each other, we saw that only 3 teams displayed a full consistency across all methods, whereas all other teams were consistent in 2 methods. The teams that are most affected by this are Wellington Phoenix and Newcastle Jets, as they alternate between the 6th and 7th positions, which is the cutoff for the final series in the A-League. Another interesting note that we found was that no team was spread across 3 different rankings, showing some level of unity among these systems.
To demonstrate the impact of the eigenvector approach on prize money, an English Premier League structure was hypothetically applied to an Australian context. This is due to both competitions, the AFLW and the A-League, not having prize money or having explicit public accounts of how the money is being distributed. The EPL uses a linear equation for distributing merit money between teams. Their equation has been adapted in Figure 8.2 relative to the A-League. As a result of this change in ranking approach, in the 2016-17 season, $1.2 million needed to be redistributed. Some teams won up to 3 times their original winnings, while others lost just as much. The 18-19 season saw a different financial impact. This season saw only 2 teams swap ranks, while all other teams maintaining their current standings. This meant only 2 teams experienced financial loss or gain, with only $300,000 being redistributed. For question 4, to determine who won the different prizes, we looked at 2 different methods that didn't see all wins and losses to be equal in value. These were Macy's method and the 2-step dominance method. When looking at the prize for best defence and worst defence, a possible avenue could have been looking at the team with the highest goals scored and the highest goals conceded. Instead, we decided to use Macy's method, a method focused on points differential, as it accounts for the interaction that these values have with each other within a game context.
Using Macy's method, we can determine the teams that have the highest and lowest points differential by taking the difference in points each round for each team. We then set this up as a set of simultaneous equations and convert that to the form of the matrix A multiplied by X, a set of variables, and then equal that to the points differential per team. After taking the transpose of matrix A in the previous slide, we then multiply that by A to find the Massey matrix, where the Massey matrix is an n by n matrix where n is the number of teams in the competition. After calculating the Massey matrix, we then use that to find out the points differential by multiplying it by matrix B, and where matrix B is the points differential per round of the competition. After calculating the points differential, which is matrix C, we then can set up the equation to find the Massey ranking, where C is equal to M multiplied by T, where T is the Massey ranking for each team. After doing this, we can then rearrange to find T by dividing matrix M and C to calculate the Massey ranking for each team. By taking the division of matrix M and matrix C, we have calculated the Massey value in MATLAB. From this, we can determine the team with the best offense and the worst defense. This turns out to be the Adelaide Crows with the best offense and the GWS Giants for the worst defense. This corresponds to the same as the point differential ranking, where the Adelaide Crows had the highest points differential of all their matches and the GWS Giants had the worst defense. Using Massey's method in the A-League was a little more challenging than in the AFLW. This is because the A-League play each other 3 times per season. To get around this, we take the sum of those 3 games for each team and use that as the points differential when they play each other. By taking the sum, it makes it easier to calculate the Massey matrix. We then calculate the Massey matrix as in the same way that we did in the previous slides. From here, though, we end up with 2 teams that have a points differential of 0. To get around this, by replacing the nth row of the Massey matrix with 1s, we avoid infinities arising in the calculation of x equals m divided by c. In the previous slide, by setting the last row of matrix M to 1s and the last row of matrix C to 0, we get around the fact that matrix M was not originally invertible. Because of this, we can now calculate the Massey rankings for each team, and we find that the Sydney FC have the highest Massey ranking with the largest point differential, and Newcastle Jets to have the lowest Massey ranking with the lowest point differential.
For the second prize, the two-step dominance method was used. This method analyzes how teams fared against tougher or easier teams. It does so by placing a value on each team's win, so we can see how each team fared throughout the season in tougher situations. To obtain the rankings provided by the two-step dominance method, a key calculation is required. This calculation uses the same augmented matrix A from the eigenvector approach. From this matrix A squared plus A is calculated, producing the two-step dominance ranking values. From the calculations conducted, Sydney FC ended up on the top of the ladder, making them the most likely from that season to beat the tough teams. On the opposite end, Central Coast Mariners were the most likely to lose to the easiest teams. Thanks for listening, everyone. I hope in the short time we had, we managed to provide you some insight into the ranking systems of the A-League and the AFLW. Cheers, guys.